Hey everyone, thank you so much for being here today. My name is Marat. I'm a managing partner of a venture capital fund, Good News Ventures, and I'm genuinely excited, honestly a little nervous too, and to share this presentation with you. Today's talk is regarding legendary properties of bismuth, electrostatic inertia, and the new technological revolution. Now, that's a big title, I know, but I think by the end of this hour, you'll agree it's not an exaggeration. Bismuth has been floating around in frontier science folklore for decades. Most people know it as a cool rainbow-colored crystal you can grow in your kitchen. You've probably seen it on Reddit or YouTube, those beautiful staircase like metallic structure with rainbow colors. Maybe some of you even grown them yourself. But there is something much deeper going on with this element, something that I believe has been staring us in the face for a very long time. And that's what we're going to dig into today. So yeah, let's get on right. So here's our roadmap for the next hour. I've broken this into several acts, kind of like a movie, because I think the story really does build that way. We're going to start by asking a really simple question that nobody seems to ask. Why does bismuth grow the way it does? No, not what happens, but why. There's a big difference, and we'll get into that right away. Then we'll build up on what I believe is the hidden fundamental property behind it all. Something I'm calling electrostatic inertia. After the theory, I'll show you how mainstream science has actually been catching up to some of those ideas with papers from Princeton, McGill, and KIT, all published actually in the last few years. Then we'll talk what all that means. We'll look into real-world application and that already using bismuth in ways most people don't know about. And we will explore some genuine strange anomalies in nuclear physics, and we'll end up in frontier territory with a kind of personal call to action. So let's get into it. So let's start with the obvious. Yeah, bismuth is beautiful. If you ever seen one of these crystal in person, you know what I'm talking about. It's honestly one of the most visually striking things in all of nature. The colors come from a thin oxide layer, and they change depending on the angle. It's like holding a tiny piece of a rainbow. And it's well known that bismuth is the most diamagnetic element at room temperature. That means it repels magnets. But here's the thing. Everyone talks about what bismuth does and what it looks like. Oh, it's diamagnetic. Oh, it grows Hopper crystals. Oh, look, pretty colors. Fine, but nobody seems to ask the deeper question. Why does it grow this way? Why this specific shape? Why this specific geometry? Why is this the most diamagnetic element at, not say, lead or gold? So today we explore why. Okay, so here's where we start challenging the conventional narrative, so to speak. When you look up a bismuth crystal in textbook or on Wikipedia, they'll tell you that those are called Hopper crystals. The explanation goes something like the edges of the crystal grow faster than the faces, so you get the stepped staircase-like structures. The center of each face sinks inward because it can keep up with the edges. And look, that's true. That is what happens. Observationally, it's accurate, but it's a description, not an explanation. It tells you the mechanism, but not the cause. It's like asking, why does it rain, and getting the answer because water falls from clouds. Okay, great, but why is the water up there in the first place? What actually driving this? I like to compare it to a tornado, a spinny wind. Technically correct, fundamentally useless for understanding why it forms, where it goes, and how to predict it. So what I want to do today is go beyond this description to get to the actual cause. Why do the edges grow faster? What's driving the specific geometry? What fundamental principle is at work here? Because once you answer the question, everything else about bismuth, the diamagnetism, the expansion, the extraordinary stability, it all starts to make sense as part of one unified picture. And that's way more satisfying than edges grow faster. All right, so Before we go further, I want to give you a quick terminology guide because I've deliberately translated some concept into more accessible language for today. I don't want anyone to feel lost because of jargon. So the core idea today comes from a theoretical framework that uses the term dielectric inertia. For our purposes, I'm calling it electrostatic inertia. Same concept, just easier to grasp if you're not kind of steeped in that particular framework. And again, credits where credits is due. This framework builds heavily on the work of Ken Wheeler, on Missing Secret of Magnetism, Tesla, Steinmetz, among others, and I'll have full acknowledgement at the end. So when I say electrostatic inertia, what I mean is this: Bismuth internal field state is so saturated, so incredibly full of stored energy that it resists any external attempt to disrupt it. Think of it as the electromagnetic equivalent of a spinning gyroscope. But we'll get deep into that analogy later. It's going to be the key to everything. Similarly, where the original framework talks about counter space, I'll say convergent geometry, meaning inward collapsing. And where it says spatial, I'll say divergent, meaning outward expanding. Just two directions of the same fundamental force. Think of it like a breathing in, breathing out. Bismuth is the ultimate breathing in. So keep those terms in mind. They'll keep coming back throughout the talk. So here it is, the core claim of my entire presentation. If you take one thing away from today, let it be this slide. So I'm proposing that bismuth primarily property is not diamagnetism. Diamagnetism is the secondary effect. It's the consequence. The primary property, the thing that actually drives everything, is what I'm calling electrostatic inertia. So let me break it down in simple terms. Electrostatic inertia means that internal electrostatic field of bismuth is so incredibly saturated, so completely full, that it actively resists being charged by anything external. It's at maximum capacity. There is no room for anything else to get in and rearrange it. So when you bring a magnet near bismuth, the bismuth doesn't repel it in the way we normally think of repulsion, like two magnets pushing each other apart. It is more subtle than that. It just refuses to participate. It won't let its internal field be rearranged. It won't align. It won't play along. And that stubborn refusal is what we observe and measure as diamagnetism. So here is the key reframe. And please really let this land. Bismuth is not diamagnetic by nature. It's diamagnetic by consequence. The diamagnetism is a symptom. Electrostatic inertia is the cause. Flip this around in your head, and suddenly bismuth goes from being a kind of curiosity to being one of the most important elements on the periodic table. So now let's look at where bismuth sits on the periodic table, because its position is honestly kind of miraculous. It's been placed there by design. Bismuth is element 83. It has 83 protons and 126 neutrons. And 126 is what nuclear physicists call a magic number. It's one of those specific neutron counts that makes a nucleus extraordinarily stable. It's like hitting the jackpot in nuclear physics. But look at its neighbors. I mean, really look. To the left, you got lead, toxic, thallium, even more toxic. One of the classic poisons. To the right, polonium, one of the most radioactive substances. And then astatine, even worse, so unstable, barely exists in nature. And right there in the middle of this toxic radioactive war zone sits bismuth. Perfectly stable, perfectly harmless. You can literally drink it as medicine. And get this, if you add just one single proton to bismuth, you get polonium. One proton. That's how razor thin the balance is. And its half-life is roughly 1 billion times the age of the entire universe. For all practical purposes, it lasts forever. And it's quite rare, about 9 parts per billion in Earth crust. This is not an ordinary element. Now, this gets really interesting. There are three angles that show up all over nature, and they are all connected to golden ratio. Some of you may be familiar with some of these. First is 137.5, the golden angle of growth. This is the angle you see in phyllotaxis, which is like how leaves, seeds, and petals arrange themselves on plants. If you ever counted these spirals on the sunflower head or a pine cone, you've seen these angles in action. It's nature's way of optimizing growth, packing the most stuff into the least space, galaxies and other things. Second angle, 85 degrees, what I call the golden angle of life. It shows up as a foundational angular constant in biological structure, related to complement of golden angle. And the third angle is 108 degrees, the golden angle of manifestation. This is the interior angle of a regular pentagon, appears throughout sacred geometry, very close to the bone angle in a water molecule as well. And here is the prediction that made this framework testable. If bismuth crystal geometry is really governed by a fundamental field principle and not just random edge growth rates, then the same golden angles should appear in structure. And it's been tested. Well, we'll get to the result in just a moment. So I want to introduce you a framework that's really helpful for understanding what's going on. Think of two fundamental direction in nature, two ways that energy can move. On one side, you have what I call space or divergent geometry. This is outward expanding, centrifugal. This is magnetism. Think of magnetic field lines radiating outward from a magnet. Like this is pyrite, which grows in perfect cubes, geometry pushing outward from a center point. On the other side, you have convergent geometry, inward, compressing, centripetal. This is electrostatic field that I'm talking about. Energy pulling inward, collapsing toward a center. And this is bismuth, which grows is what I call anticubes. The geometry is pulling inward, not pushing outward. And the beautiful thing, the same golden ratio governs both directions. The same mathematical principle expressing itself in two opposite ways. Pyrite and bismuth are like the inhale and exhale of the same breath. So, about that term, anticube, I really don't think Hopper crystal is the right name for what bismuth does. I think a more accurate and more meaningful geometric description is an anticube, or if you prefer the mathematical term, a hypercube, tesseract. And this isn't some new idea. 500 years ago, Leonardo da Vinci illustrated something called the solidus for the book of the Divine Proportion. The solidus is essentially the cube of space, the outward geometric expression, the framework of expansion. Look at bismuth crystal. Really look at it. It's not pushing outward like a normal crystal. Every phase is sinking inward. Every step goes deeper. It's collapsing toward its own center. The stepped staircase geometry that everyone finds so beautiful. That's not a growth defect. That's the physical expression of an inward collapsing field. That's convergent geometry made solid. When you hold a bismuth crystal, you're holding the geometry of electrostatic inertia frozen in metal. So, okay, so all of this theory so far. Interesting theory, hopefully compelling theory, but still theory. The real question, can we test it? And the answer is yes. So I did it. So this is an anti-cast experiment, and it's been done not only by me, it was done by Ken Wheeler and other folks that I know. So the idea was straightforward. If bismuth geometry is truly governed by golden ratio angles, then when you force bismuth to solidify in a controlled environment, the angle should physically appear in the solid. You should be able to measure them. So here's the process. Melt bismuth. It's pretty low temperature for a metal, only 271 degrees Celsius. Pour it in a preheated aluminum mold. Like you can use it at the bottom of a can of a beer. And then preheating is really important. It prevents thermal shock and creates a more uniform cooling gradient, which lets the field geometry express itself more clearly. And here is what happened. The casting showed large divots, if you are in a triangular shape, and inertial patterns forming at precisely 137.5 degrees and 85 degrees, the golden angles, exactly as predicted by the theory. So I measure them. They are all real. They are reproducible. and then they appear exactly the position the framework predicted they would. All right, so here's another amazing property that fits perfectly. Bismuth expands when it freezes by approximately 3.3%. The liquid is actually denser than the solid. And in the context of this framework, it makes perfect sense. As bismuth cools and solidifies, the electrostatic inertia, that inward pulling convergent field, actually forces the crystal lattice to expand as it locks the field geometry in place. The field demands more space to express itself. But here is what really wild part. The solid seems to remember the field state of the liquid. Bismuth cools from the center outwards. And as it does, the geometry of the internal field gets frozen into the crystal structure. The solid becomes a permanent record of what the field was doing at the moment of solidification. Now, well, it sounds like a bold claim, but in 2017, a team published a paper in one of the most prestigious scientific journals in the world that proven exactly this. In 2017, a team from Yenshan University, the University of Chicago, and the Carnegie Institution published a paper in the Proceedings of the National Academy of Sciences. They took bismuth, remember, the single most diamagnetic element that exists, and they made it ferromagnetic. They literally flipped its magnetic behavior from one extreme to the other. How? By controlling the solidification process. They heated bismuth way above its normal melting point, past 1200 Kelvin, and then quenched it rapidly, cooled it super fast under pressure, and the resulting solid was ferromagnetic, not diamagnetic, ferromagnetic. So what that means for us? Well, the most magnetically resistant element in nature can have its field state completely reversed if you control how it solidifies. But the same paper found something even more profound, and this is the part that really connects to the framework. They discovered that liquid bismuth undergoes what's called a liquid-to-liquid phase transition at around 1200 Kelvin. The liquid itself fundamentally restructures at that temperature. It's not just getting hotter, it's reorganizing internally. And when they rapidly cooled it after the transition, the solid remembered the structure of the high temperature liquid state. The paper literally uses the phrase structural memory effect. This was the first time this had ever been observed in any pure element, ever. So the solid remembers the liquid. They called it a pathway in tailoring physical properties, quote unquote, meaning they recognize this could be used to engineer materials with specific characteristic just by controlling how the liquid solidifies. Moving on to this, another major validation. In 2022, a team at Princeton discovered that bismuth functioned as a topological insulator at room temperature. This was published in Nature Materials. Now, for those who aren't familiar, what's a topological insulator? Think of it this way. It's a material that's an insulator on the inside. Electrons can flow through its bulk, but it conducts perfectly on its surface. It's like a ball that's made out of rubber on the inside, but coated with copper on the outside. The surface and the bulk behave completely differently. This is a quantum mechanical phenomenon. It's usually only observed at extremely cold temperature, and we're talking near absolute zero. But bismuth does it at room temperature. No special cooling required. That's a very big deal for potential application. And then in 2025, team at McGill University in Montreal published in Physical Review Letters showing something called the temperature-independent anomalous Hall effect. Temperature-independent is the key phrase here. It means that quantum behavior persists regardless of how much thermal energy you throw at it. Normally, heat disrupts quantum effects. In bismuth, the quantum state just doesn't care. If that doesn't sound like an inertial refusal to you, I don't know what does. The internal field state is so robust, so locked in, that even thermal noise cannot disrupt it. That's electrostatic inertia observed, measured, and published, but they just don't call it that way. Third validation made in February 2025, just a year ago. A team at KIT Technology Institute in Germany synthesized something called a B5 minus ring. Basically, 5 bismuth atoms arranged in a ring. Why should we care? Well, because it's the heaviest analog of something called cyclopentadienyl ever created, one of the most fundamental building blocks in organometallic chemistry, and now we have a version made of bismuth. The ring is aromatic, meaning the electrons are delocalized around the ring, just like in benzene. Opens up enormous landscape for potential chemistry, exploring application batteries, catalysis, gas storage. So the chemistry of bismuth is just getting started. For an element that's been known for centuries, we barely scratch the surface, and that to me is incredibly exciting. Well, bismuth isn't just a theoretical curiosity. It's already doing extraordinary things in the real world today. Nuclear reactors, thermoelectric generators, medicine. Bismuth is already there, working, doing its thing. Industry has been exploiting its unique properties for decades. They just haven't connected dots as to why these properties exist. And I think electrostatic inertia explain all of them. So the bismuth material properties are kind of insane. Melting point of only 123 degrees Celsius, stay liquid at relatively low temperatures, which mean easy startup. Boiling points at 1600 Celsius, excellent gamma radiation shield. It doesn't react with water or air. So basically, it's a perfect nuclear coolant. But here is the part that's interesting. The lead bismuth eutectic is an excellent shield against gamma radiation, but it's virtually transparent to neutrons. Neutrons pass right through. It's like it's not even there. Now think about that through this framework. Gamma radiation is electromagnetic. It's divergent, it's spatial energy, outward expanding. Bismuth blocks it cold because its convergent field opposes divergent energy. But neutrons are not electromagnetic. They are on the convergent side of the duality, the same side as bismuth's own field. So they pass through unimpeded. Like recognizes like. Next up, thermoelectrics. Bismuth telluride has been the gold standard thermoelectric material since 1950s, over 70 years, and nothing has beaten it. Its Seebeck coefficient is around 250 microvolts per Kelvin, which is outstanding for converting temperatures differences directly into electrical voltages. Every portable cooler you've seen at the tailgate on a camping trip, probably running on a bismuth telluride via the Peltier effect. Many satellites power system, same material using the Seebeck effect in reverse. The fact that bismuth sits at the heart of the best thermoelectric material we've ever found is not a coincidence in my view. Its saturated electrostatic field properties make it uniquely suited for mediating between thermal and electrical energy. And here's my absolute favorite fun fact about bismuth. It's the only non-toxic heavy metal. Let that really sink in. Pepto-Bismol, the pink stuff you drink when your stomach is upset, has been around since 1919, like over 100 years. You literally drink a heavy metal compound and it makes you feel better. So, but again, look at the bismuth neighbors on the periodic table. Lead, toxic, causes brain damage. Thallium, nicknamed the poisoner's poison, one of the most lethal element known. Polonium, highly radioactive. And right there in the middle of this, bismuth, safe enough to sell at CVS. Why? How is that possible? Again, electrostatic saturation prevents harmful biological binding. The internal field is so locked in, so inertially stable that bismuth simply cannot interact destructively with biological molecules. It's too full, quote unquote, to participate in toxic chemistry. All right, so we've seen the practical side. Bismuth already working in the real world. Now let's go deeper into territory that's genuinely strange. So there are 4 natural radioactive decay chains in nature, 4 series of unstable elements that progressively decay through alpha and beta emission until they reach a stable endpoint where the decay stops. 3 of them end at lead. The thorium series ends at lead 2A, the uranium series lead at 206, actinium series at lead 207, lead, lead, lead. Stable, unremarkable, done. Lead is the default good enough endpoint, stable enough that the decay process stops. But the 4th, the neptunium series, ends at bismuth 209, not lead, bismuth. So think about what that means. In 3 out of 4 cases, nature radioactive cascade settles into lead, which is perfectly stable. But in one special case, nature goes one step further. It doesn't stop at good enough. It reaches bismuth, the heaviest stable element in existence, the maximum possible electrostatic saturation point. Bismuth isn't just another stable endpoint. It's the ultimate endpoint, the place where nature's transmutation process finally, completely, definitely stops. As far as we know, there is nowhere else to go. I really don't think that's a coincidence. Here's an anomaly that really makes you stop and think. The bismuth 209 nucleus has a higher total energy than the sum of its decay products, thallium 205 plus an alpha particle. In normal nuclear physics, when a nucleus decays, it releases energy precisely because the products are more stable, lower energy than the parent. The products weigh slightly less than the parent, and the missing mass becomes energy via E and mc squared. That's how nuclear power works. Parent heavier, product lighter, difference equals energy release. But with bismuth, that math goes backwards. The nucleus appears to contain more energy than what you would need to assemble it from its component parts. It's like a battery that somehow holds more charge than was ever put into it. Mainstream physics handles this by noting that bismuth 209 has a very, very slight alpha instability, hence the absurdly long half-life. Fair enough, that's accurate. But in this framework, this makes even deeper sense. The electrostatic field is saturated beyond the normal equilibrium point. It's overcharged. The extra energy isn't a mystery. It's the inertial tension of the saturated field itself. It's literally a nuclear scale field battery running at 100% capacity. Well, this is the most important analogy in the whole talk. So I want to really take our time with it. Think about a spinning gyroscope. When a gyroscope is spinning fast, it does something magical. You can push it, you can tilt it, you can tilt the surface it sits on. You can even try to turn it sideways, and it just keeps pointing the same direction. It resists being reoriented. But, and this is crucial, it's not pushing back against you. It's not generating counterforce. Its angular momentum creates an inertial state that simply refuses to change. It's not fighting you. It's just not participating. It's locked in. Bismuth does the exact same thing with magnetic fields. When you bring a magnet close to bismuth, bismuth doesn't actively push the magnet away like another magnet would. Its internal electrostatic field is so saturated, so completely locked in, that it simply refuses to be rearranged. The field won't align. It won't budge. It's inertial refusal, not active repulsion. This distinction matters enormously. Repulsion implies an active expenditure of energy. You push me, I push you back. Inertial refusal is completely different. It's passive. It's just a state that happens to resist change, like a gyroscope that happens to not fall over. And here is where the paper connects beautifully. They proved that you can overcome this refusal if you apply enough pressure and heat, extreme conditions, just like a gyroscope. If you grab a gyroscope and really force it, With enough sustained torque, you can eventually tip it over. The analogy holds perfectly at every level. So when someone says bismuth repels magnets, that's not quite right. What's really happening is more profound. It's a gyroscope that won't budge. So if bismuth is this saturated, inertial locked field state, what does that really mean in terms of energy? I want you to think of it as a battery, a fully charged battery of electrostatic field energy. An atomic number 83, bismuth sits an absolute limit of nuclear stability. It's packed with as much potential kinetic energy as nature can cram into a stable configuration without it tipping over into radioactive chaos. As we know, thanks for the researcher teams, that you can flip its field state, the battery can be switched diamagnetic to ferromagnetic and presumably back again. The energy is in there and the state can be changed. So the obvious question becomes, what if you could tap that energy? What if you could find a controlled way to release the stored inertial tension? Not destructively, like a detonation, but in a controlled, repeatable way. That's where we move from observation into hypothesis. And again, I want to be very clear and honest about this. What follows is speculation. It's informed speculation, grounded in everything we just reviewed, but it's speculation nonetheless. Keep that in mind. So, so if someone wanted to actually test this hypothesis, here's the free stage roadmap I came up with. Stage one is, I think, probable cause of field manipulation using Hallback arrays, golden ratio geometry to create precise field condition around bismuth samples. We know from the casting experiments the golden ratio spacing is fundamental to how bismuth responds to fields. The stage is about getting, I guess, the geometry right. Another experiment is the electrostatic saturation, charging the bismuth to its lattice limit with high voltage. Again, the team at the PNAS results validate this kind of extreme approach can fundamentally alter bismuth field behavior. We need to explore the parameter space. And stage three is proton bombardment, stressing the nucleus right up to the edge of instability. This is the most ambitious stage, I would say, and it's where we need real experimental physicists, people with access to accelerators, high voltage equipment, and the expertise to do this safely. So pulling all of this together, where does everything we've discussed today actually lead? I see 5 major application domains. Propulsion, using convergent geometry principle for fundamentally new forms of transportation. Energy, harnessing electrostatic inertia for clean, powerful energy generation without combustion or nuclear fission. Materials, programming materials at the field level rather than just the chemical level, creating a whole new class of engineered metamaterials. Computing, bismuth topological insulator properties make it a genuine candidate for room temperature quantum computing substrates. And again, medicine beyond peptide bismuth, targeted bismuth nanoparticles for drug delivery, imaging, and therapy. Every single one of these is grounded in research we discussed today, and then this isn't science fiction. So if I had to distill the entire presentation down to one sentence, one takeaway, it would be this. Bismuth is the purest expression of extreme electrostatic inertia in the periodic table. Not the densest element, not the rarest, not the strongest, but the most electrostatically saturated stable element in existence. And every single anomaly we discussed today, the crystal geometry, the diamagnetism, the expansion and freezing, the structural memory, the non-toxicity, the decay chain endpoint, the overcharged nucleus, the topological insulator behavior, every single one flows from this single underlying principle. One cause, many consequences. That's the, I guess, hallmark of a good theory. Yeah, but here's the kicker, and I want to leave you with this thought. Everything I talk about today, like electrostatic inertia, convergent geometry, field saturation, this is just one of 4 fundamental field modalities, 1 out of 4. And Bismuth is the purest expression of one of them. But there are 3 more, and when you understand all 4 and how they interact, how they conjugate, how they create the phenomena we call magnetism, electricity, gravity, and matter, you'll start to see a unified picture of physics that's far more elegant, far more powerful than anything in the standard model. That's the material for my next presentation, I guess. But today was the gateway. Bismuth was the kind of foot on the door, the most tangible, most beautiful, most accessible expression of this deeper reality. And I hope I've shown you that the door is worth walking through. Yeah, here are the key reference for everything I've covered. I would specifically encourage you to read Ken Wheeler books, Uncovering the Mystic of Magnetism, PNAS paper, Princeton, McGill, key papers are all searchable throughout the respective journals. And Ken Wheeler's book is available online. Dig into this, form your own conclusion. And yeah, thank you for all spending time with me today. I know this was a lot of information, and I really appreciate you sticking with it. This is the theoretical framework is in place. The pieces are on the table. What's been missing, I guess, is the experimental side. I'm actively looking for like-minded people, physicists, engineers, experimentalists, thinkers, makers, anyone who has the hands-on capability to design and run real experiments, because the ultimate goal here isn't just to write papers about Bismuth or give cool presentations. The ultimate goal is to build a zero-point energy device, and from there to unlock interstellar and eventually intergalactic travel. I know that I know how that sounds. I know it's audacious, but honestly, every major revolution in human history started with someone looking at existing evidence and asking, "What if we push this further?" Right? That's all I'm doing. So, and yeah, and I don't want to do it alone. So here's what I bring to the table. I have capital. I have a unique perspective on possible solutions. I've spent years thinking about this framework and developing some interesting ideas. What I need are like-minded people with practical and experimental skills, people who can build the rigs, run the tests, measure the results, and help figure out what actually works. Well, if anything today resonated with you, if you felt that spark of this could be something real, please reach out. My email is on the screen, and Marat at goodnewsventures.com. I read every single message personally. And yeah, let's build what comes next. Thank you.